Hello Year 11, welcome to the fourth lesson for exercise 10D, the remainder and the factor theorem. Why have I not capitalized this? The remainder and the factor theorem. Okay, so let's talk about the two theorems. They're pretty easy to prove, so I'm going to go through the proof as well. But the remainder theorem states that for a polynomial p of x, its remainder after being divided by x minus a will be p of a. So what they're trying to say is whatever linear factor you're trying to divide it by, the value of x that makes the divisor equal to 0, so in this case x should be a, that number substituted into the polynomial will give you the remainder straight away. That's what the theorem is trying to say. Now to prove that, we know that any polynomial can be written as its divisor times the quotient plus remainder. We've done that in the last lesson. And in this case, we're calling the divisor a linear factor x minus a. So I can replace the divisor with x minus a. And then I'll just simply write the quotient as q of x and remainder as r of x. If you sub in a into the polynomial, we end up getting a over a at this point. So that whole thing is going to go to 0, which sort of cancels out the qa as well. And what are you left with? The remainder. So subbing in a would give me the remainder. Now it says r of a, so that's just whatever expression we have after substituting a. But if I already know the divisor is going to be a linear, I know that the remainder has to be less degree, because if the degree was higher, then we can divide further. So that has to be a single constant, which means it's just going to be a constant remainder. And that's pretty much it for a remainder theorem proof. So let's see what types of example questions we might get. Example 1. The question could simply ask to find the remainder when it's divided by a certain divisor. So in this case, it's going to be x minus 10. Imagine that's our x minus a, or whatever number that makes that equal to 0. Because the point was that we want to make it into a 0 so that it cancels away the quotient. So in this case, we want to sub in x equals to 10. So we can say remainder is equal to p of 10, which should be just 10 substituted into that polynomial. You guys can do it on the calculator. I think you should be getting 851. For b as well, same thing. There's an extra 3 at the front, so I can't really write that as x minus a, but it's whatever the number makes the divisor into 0. So our a is pretty much negative 2 over 3. So I can say our remainder is equal to q of negative 2/3. You've got to use the name given in the question. And if you substitute that, you get negative 137 on 9. And that's the remainder. So you don't have to do the actual long division to find the remainder. Now, why are we interested in finding the remainder? It's because sometimes the question is going to give you the information about the remainder and tell you to work backwards to find the coefficients. So have a look at example 2. They give you the function, but with some unknown coefficients. But they give you the remainder. It says when it's divided by x plus 2, the remainder is 7. So then what I can think about from just reading that sentence is that if I substitute negative 2, because that's what makes the divisor into 0, I should get the remainder 7. That equation should instantly come into your mind if you read a sentence like this. You will see a very similar type of question like this in the exam. So I could use that in part A. Maybe I'll just write it here. I'll say f of negative 2 has to be 7 because of the remainder theorem. So if I sub in minus 2 into f of x, it'll be this pretty much. And we already know it has to equal 7. And if I just simplify that, it's negative 8 plus 4a minus 2b plus 3 is equal to 7. Move all the constants to the other side, which is going to be 12. And if you divide everything by 2, you would get the desired result, which is 2a minus b is equal to 6. Boom. And then part B, it says, given that the remainder is 4 when it's divided by x minus 1, find a and b. So again, if I read that sentence, I think immediately f of 1 should equal 4, because 1 is what makes this divisor equal to 0. Subbing it into fx, I should get 1 cubed plus a plus b plus 3 is 4. Oh, it's an easy sentence. We know a plus b has to equal 0. So then, now that I have two equations in terms of a and b, I should be able to solve simultaneously. So let's label them 1, 2. I could probably just add 1 and 2 together to eliminate b. So we can say 3a is equal to 6, which tells me a has to be 2. And I can sub that into 2 maybe. Sub into 2 and get 2 plus b is equal to 0. Of course, b has to be negative 2. So see how you were given information about remainders and you were able to use that to find unknown constants or coefficients. And this is one of the most typical exam style question you might see. Easy, maybe 3 marks, even 2, because it's very routine type problem. So yeah, easy marks. Next, factor theorem, which is pretty much the same thing as a remainder theorem, but just a little bit of an extended version. If you've got a polynomial p of x, then the divisor x minus a is considered to be a factor of px if p of a is equal to 0. And the proof of this doesn't even have to be algebraic. Maybe I can just type it in. So we can say something like p of a should give us the remainder of the polynomial after being divided by x minus a. Oh, okay. And that's because of the remainder theorem. But if the remainder of something is equal to 0, then the divisor and also the quotient as well are factors. Because when there's no remainder, we say it divides cleanly, then it must be considered as a factor. So we can say, therefore, x minus a is a factor of p of x. So not much algebra needed for this one. That's pretty much it. So, if you see the word factor, then you need to instantly link it to the fact that the remainder is equal to 0. Having that in our mind, let's have a look at example 1. If the question says, determine if x plus 3x is a factor of that or not, we are not going to use long division anymore. We're just going to use the factor theorem and say whatever this divisor makes 0, so that's x equals to negative 7 on 3. We are going to sub it into our polynomial to see if it gives a remainder of 0 or not. So let's sub it in. 3 times negative 7 on 3 squared plus 7 times negative 7 on 3. If you type that into the calculator, you actually do get a 0. So then if you do, then we can conclude that the divisor was in fact a factor. Now for part B, the number we are substituting is, when this is equal to 0, so that's -12. So if we substitute it into the cubic expression, I should get a 0 if it's a factor. If you type it into the calculator, I think you also do get a 0. Or do you? Actually, I don't trust myself. Let's double check. I don't know if you can see the calculator on the screen. 4 times -0.5 cubed plus 4 times, that's just a quarter, plus half minus 1. 0. Amazing. So then I can say therefore 2x plus 1 is a factor as well. And if you get any other number than a 0, that means the remainder is there, which means your divisor wasn't a factor. Example 2. Show that x minus 3 is a factor, hence factorize fully. Okay, if I want to show that this is a factor, I'm going to have to sub in 3. Let's just quickly evaluate that. That's 27 minus 18 plus 3 minus 12. That's 30 minus 30. Easy, 0. Therefore, x minus 3 is a factor. And if it is a factor, I should be able to divide it and get the quotient to be its factor as well. So maybe I can do a choo-choo train. Let's do a quick revision of the long polynomial division. X minus 3. So matching the terms, x squared. I get x cubed minus 3x squared. Subtract x squared plus x minus 12. Match the term, plus x, which gives x cubed minus 3x. Subtract 5x. Hold on, that's not true. 4x minus 12 plus 4 will give me 4x minus 12. Of course, it has to have no remainder because we already knew it was a factor. But I can now write my p of x as x minus 3 times my quotient. And unfortunately, that's not something we can factorize. Let's quickly check the discriminant. So the discriminant is going to be b squared minus 4ac. So that's a negative number, which means there's not going to be any solutions for it anyways. And there's no solution to the quadratic formula, so you can't factorize that fully. So that is the full factorization for now. Example 3. Solve by fully factorizing. Now there's not many info given, it just tells me to solve by factorization. In this case, we need to consider the constant term. So let me just give it a name. P of x is equal to the left-hand side. If you look at this constant over here, if it's a cubic polynomial, so I know that maximum there's going to be a factorization of 3 brackets like this with x, x, x. Now, an interesting fact is whatever number I have after my x here, eventually they will all multiply to result in this constant over here. So from that fact, we can actually see that those numbers a, b, c has to be some factors of -8. Which means we can actually, maybe I'll just leave it there. So I can say A, B, C factors. And what that tells me is if I want to find or test possible factors of P of X, I will need to test factors of -8 into my polynomial. And whatever number, okay, say if I sub in a number and get a 0, then I know x minus a is a factor, right? Using the factor theorem. But the number that I sub into the polynomial, this, will have to be a factor of -8. So we're not substituting any random numbers. We are only trying factors of -8. So let's list them. Of course, 1, 2, 4, 8, right? But it's important that you test both positive and negative of that. So we're subbing in 8 numbers into a polynomial, which means it'll be handy if we can use the answer function. So hop onto a calculator and we're going to write down our polynomial, replacing x with the answer button. So answer cubed plus 3 answer squared. Oops. Minus 6 answer minus 8. And then let's try factors of -8. So let's try +1. Let's try -1. So let me write that down. We got P of -1 to be 0. Now that's going to suggest that x plus 1 is a factor. So I've already found one factor of the factorization. Let's move on to 2. Another one. So P of 2 is equal to 0, suggesting that P minus 2 is a factor. Let's try -2. Nope. Actually, I can use a strategy here. I already know the two numbers are -1 and 2. If you multiply that, that gives me -2. And knowing that it has to be -8, I know the other one has to be -4. So let's try that. -4 straight away. Bingo. So I can see that P of -4 is equal to 0, suggesting that x plus 4 is a factor. So then I can rewrite the P of x as x plus 1, x minus 2, x plus 4. So then solving for this is equal to 0 is going to be easy. X has to be -1, 2, -4, which are pretty much the numbers that I've substituted. So I already knew that there were the zeros of the polynomials, but it's for the sake of using the factor theorem. And that is it for this exercise. So your homework is to hop on to exercise 10D and try questions 6 to 16. Good luck, and I'll see you in the next video. Bye!